Great. So apologies for having to listen to me 3 times today. I'm going to talk a little bit about ways that you can optimize crystals to go from small crystals to large crystals or large crystals to small crystals. This is going to focus a lot on sort of general principles. And the thing that I really want you to take away from this lecture is that you can make use of a phase diagram to figure out sort of which direction you want to go and how to improve the size of the crystal to match the experiment. So we talked earlier today about initial identification of crystallization conditions. So you throw a broad chemical net, and hopefully the sampling is such that you end up identifying a chemical condition, a cocktail, where your protein will form ordered aggregates which grow into crystals. Okay, so we're going to assume that we've sort of reached that step and that we've gotten at least one, hopefully more, chemical conditions that will produce crystals of the protein at this step. Again, this is going to focus mainly on soluble proteins. I'm not going to get into protein modifications that might be required to improve the quality of the crystals. Those are very important, and they're definitely not something that's mechanical. The screening process is very mechanical. You typically have a set of favored cocktails that you run your protein through, and you see if you get crystals to form. This optimization step is much less mechanical. There are methods available, but those methods don't always work. So a lot of times it involves a lot more thought. So going to a quote that I love that's back from 1951, it's basically saying that if you want to produce large crystals, then you need to pay attention to the salt concentration, the pH, the protein concentration, and the temperature. These variables are very important, and they apply whether you're trying to produce a batch of large crystals or a batch of small crystals consistently. So any of these factors that can affect protein solubility are going to have a dramatic impact on the optimization of the crystal volume. So most of the time, for most labs, they're trying to go from producing smaller crystals to producing larger crystals that diffract X-rays to higher resolution maybe, and or better optical quality sometimes, which doesn't always coordinate at all with the diffraction quality. But for XFELs, we're typically trying to identify and optimize conditions to produce a large number of small crystals. Now, this is assuming that we're not going to crush up crystals to get the nanocrystals that are used for XFEL's diffraction by mechanical crushing. So, okay, so optimization. After you identified some initial conditions, then you're basically going to focus on changing, altering, adjusting the level of protein supersaturation. So this is, you can break it down into 3 basic things. You've got how rapidly the protein reaches a state of supersaturation, the path that the protein takes to get to that point of supersaturation, and the level, or how supersaturated the protein is in this experiment drop. So all 3 of those things are going to affect the volume of the crystal that you form. So everything goes back to a simple phase diagram. And these protein phase diagrams that I'm sure you've all seen before, they really combine thermodynamics and kinetics. And they don't always make that clear in a lot of the discussions that you hear or the papers that you see. But basically, a phase diagram is just a collective view of the outcome of your crystallization experiments. And it's going to show how the protein's supersaturation or level of solubility relates to its chemical or physical environment. Okay? So 3 basic outcomes that we're going to focus on today are clear drops, crystalline, crystal-containing drops, and drops that contain an amorphous precipitate. Okay, so if we just think about this, not in terms of some sort of phase diagram that's very abstract, but in terms of some actual experiment outcomes, you can see in this image that or in this graph, that this particular protein crystallized from relatively high concentrations of PEG 400 or produced precipitate, amorphous precipitate. At lower levels of PEG concentration and at a more neutral pH value, it produced visible crystals. And as you got into higher pH values and lower concentrations of the precipitant, the PEG 400, you produce clear drops. Okay, so it's pretty easy to look at this and sort of have an idea and understand how these things relate to one another, right? So the number and size of the crystals that you produce is going to be dependent on how far you drive these crystals toward a condition where they're more supersaturated, closer to this precipitation boundary. Okay? If you want to produce, again, smaller crystals, you want to drive it to a higher level of supersaturation toward the precipitation boundary. If you want to produce fewer, larger crystals, you're going to want to move toward these clear drops, not to the point where you reach clear, but drive it in that direction to decrease the level of supersaturation to hopefully produce fewer crystals, larger crystals. So now to take that sort of concrete idea and sort of put it in a little bit more of an abstract view. So this is a representation that's commonly used for a phase diagram for crystallization. Okay, two main axes here. You've got the protein concentration, a function of the protein concentration on the y-axis, a function of the precipitin concentration, something that drives the protein to supersaturation on the x-axis. And at the origin, you basically have water, right? So you have the ultimate dilution of the protein and the precipitating agent, right? So we're just decreasing the concentration until we get to water. And you've got different levels of supersaturation that are represented in this diagram. First, you have undersaturated, where the protein is perfectly happy it's in solution. Protein molecules are basically repelling one another in the solution. Okay? Then you have a saturation line. And this saturation line is something that's actually been measured for some proteins experimentally. The saturation line actually represents a single crystal form that's in a state of equilibrium with the solution around it. So when you have a protein crystal in a solution, you see it in your experiment drop, it's not that every bit of protein in that drop is in the crystals. Okay? You've got an equilibrium state. We've got protein in the solution and protein in the crystal, and it's a state of dynamic equilibrium with the protein molecules coming on and off the surface of the crystal. So to actually experimentally measure the saturation line is very complicated, because you have to make sure that you've actually reached this sort of point where you've got protein molecules adhering to the surface of the crystal and protein molecules leaving the surface of the crystal. So you approach it typically from two directions, one where you're dissolving the crystal and one where you're actually increasing the level of concentration so the crystal grows. And you end up reaching this asymptotic point that you can measure experimentally. Again, it takes quite a bit of effort to do this. It's only been done for a few proteins, but it can be done. And okay, now we move into this precipitation zone. So now we're going into the very highly supersaturated zone. This is a point, they can call it spontaneous decomposition. But basically the protein is so supersaturated here that it just ends up aggregating in an amorphous way. It's just random aggregation. It comes out of solution. It's non-crystalline. Okay, then we get into this region here where we've got this sort of dotted line. And this is just strictly kinetics, okay? This is the probability of having a nucleation event, something where the protein molecules come together in an ordered way that can actually be stable enough that it can grow into a crystal. Okay, so this nucleation zone, this labile zone, is where we have ordered aggregation of the protein. Okay? And again, it's a time-dependent process, and we go to this growth zone, okay, which is adjacent to it. Again, this is represented as a gradient because there isn't really a defined tight boundary here. For one thing, so many variables can affect it that it's very difficult to measure it accurately. But for another thing, it's based on a stochastic event, a probability, that you actually have the molecules come together and form a crystal nuclei. So if you're very supersaturated, then you have many more times that the protein molecules are coming together and aggregating and can actually form something that's a viable nuclei that can grow into a crystal. But if you're in this growth region, then the probability of having the molecules come together in an ordered way is so remote that it's basically never going to happen. So if you look at a solution that's actually in this metastable zone, it'll look like a clear drop under the microscope. It will look exactly the same as an undersaturated drop. It will look exactly the same as a saturated drop. So these all appear to be clear drops when you're looking under a microscope at them. Okay? So you really can't readily distinguish between them. Some variables for optimization. So anything that affects the protein solubility is going to affect optimization. Any variable that affects how quickly the protein supersaturates on the path that it takes to supersaturation. These are all going to affect the optimization of the crystals. Okay? And many of these variables are going to be interdependent. So you're going to have, the temperature will have an effect on solubility. The chemical concentrations will have an effect on the solubility. And the way that you basically combine the chemicals together to reach that point of supersaturation, the crystallization method, will also have an effect on the outcome of the optimization experiments. Okay, so we're just going to talk quickly about crystallization methods. I'm just going to talk about two of them that are commonly used. And this is just a means to apply the chemical variables or the physical variables to affect crystallization of your protein. It's going to determine the path and the rate of the supersaturation event. Right? So the crystallization method is a dot product of the kinetics of supersaturation, how quickly the protein reaches supersaturation, and the path to supersaturation. Different crystallization methods and different modifications of crystallization methods, of which there are many, they're all designed to affect particular variables. So certain crystallization methods are very good at looking at things like the rate of the approach to supersaturation. Things such as vapor diffusion experiments or liquid diffusion experiments, where you can have some control using diffusion gradients or some other ways to limit the rate of equilibration of that droplet. Whereas other methods like batch methods, if you're just looking at batch at one temperature, it's going to very quickly hit the level of supersaturation right at the beginning of the experiment, because you're sort of crashing the molecules together, chemical and the protein. Okay. So most crystallization methods are going to have some kind of a set endpoint, and for the most part, many methods, the kinetics of the equilibration can be controlled in some manner. Okay, so again, not to beat on this too much, but the path, the direction it will take to get to this nucleation label that you want to be in to produce your single crystals is going to be very important. And how quickly you reach that point is going to be very important. Okay? And you can break almost any of the crystallization methods that are out there in the literature. And this is just talking about standard methods. It's not talking about LCP and other types of things. But basically, most experiments can be broken down into either batch experiments, where you're just taking the protein and combining it with the cocktail, some kind of a vapor diffusion experiment, which I'll talk about in a minute, or a liquid diffusion experiment like dialysis, or some of the methods that have been developed by Juan Garcia Ruiz, where he uses these gradient methods to actually sort of have a wave of supersaturation. We're not going to talk about liquid diffusion today. We're just going to talk about batch and vapor diffusion just to save some time. So basically with a batch experiment, you're taking your protein, you're taking a crystallization chemical, your cocktail, you're combining them, and you're landing someplace in the phase diagram when you do this, right? You're hoping that you're landing in this Levau zone where you get some spontaneous nucleation event to take place. And if things work out right and you happen to hit this point where you get a nucleation event, then the concentration of protein in the solution is going to decrease slightly every time there's a nucleation event, and eventually you'll reach a point of supersaturation, or a level of supersaturation where no further nucleation events can take place, and whatever crystals have nucleated, they're going to grow to a larger size. So the location, where you happen to land when you throw your dart at the phase diagram here, that's what's going to determine basically how many crystals you have and the ultimate volume of the crystals to a large extent. And so if you're very close to the metastable zone where you can't really have any additional nucleation, then you're only going to have a few crystal nuclei that form. It decreases the protein concentration slightly in the solution. You enter the metastable region, and these crystals can then grow to a large size without competition from additional nuclei. If you're very close to the precipitation zone, very highly supersaturated, you're going to have many, many nucleation events take place. And these are actually very small crystals of this protein. Temperature effects are incredibly important, but they're very difficult to effectively take care of technically. The reason that most crystallization experiments take place or are recorded either at 4 degrees or room temperature is because those are the temperatures that people have to work in. So temperature has a huge effect on protein solubility. There's this great paper that came out years ago by Christopher that talks about the majority of proteins are going to have a temperature-dependent solubility. Some proteins are more soluble at lower temperature, some proteins are more soluble at higher temperature. It's an effect that's not protein-dependent, but protein plus chemical environment dependent. So if you have a protein with a particular cocktail, it might be it might produce clear drops at 4 degrees, precipitate, or come out of solution because it's very highly supersaturated at the warmer temperatures. But you could take that same protein with a different chemical cocktail, and have the exact opposite happen, where it's very soluble at the warmer temperature and comes out of solution very readily at the lower temperatures. So temperature has a huge effect, but it's difficult to study because you have to be able to actually extract the crystal and use it, somehow preserve it for your diffraction experiment, either at cryopreservation or something, so you can get it to a beam to actually do the experiment, the diffraction experiment. So most places will have a room that's at 4 degrees and at room temperature, but finding temperatures in between those is rather difficult, and it's typically pretty unpleasant to be working at some of these temperatures. So temperature is a great important variable. You have to be aware of its fluctuation when you're doing these experiments. Air conditioning in a building is typically not all that great for controlling the temperature tightly, but it's not something that's very practicable to actually use as a variable a lot of times for most labs. Vapor diffusion experiments, you're basically taking your crystallization drop, your protein and your cocktail, you're combining them, and you're putting them over a reservoir solution. The reservoir solution typically is the same solution that you have in your crystallization cocktail, but it doesn't have to be. It can be anything. The sole purpose of this reservoir solution is to pull water away from that experiment drop and dehydrate it. And as that drop dehydrates, it's going to increase the relative concentration of all the chemicals in the drop, including the protein. So the drop dehydrates and increases the chemical concentrations, and it drives the protein to a state of supersaturation, if you're fortunate. This reservoir solution is going to set the endpoint rate. So once the vapor pressure of water over the experiment drop in the reservoir is equalized, then it's just going to remain at that state, except, of course, the plastic plates and everything with water, so over time, things will dry out on you. Okay. So vapor diffusion experiments, typically you're going to start off undersaturated, you combine your protein with your cocktail. Now think about this, you're taking your protein, adding your cocktail. This point is basically where you're starting off if you're doing a batch experiment. You're taking the protein, adding it to your cocktail. But with vapor diffusion, you're driving it, and by dehydrating that drop, you're forcing yourself into higher levels of supersaturation, at least hopefully, and you're piercing into this labile zone where you can have a nucleation event, and then subsequent crystal growth of, if you're trying to grow just a single large crystal, hopefully a single large crystal. So the rate of equilibration can have a terrific effect on how many crystals you produce. So generally speaking, the faster the equilibration rate, the faster that drop dehydrates, the smaller the crystals you're going to end up having formed. Okay? This is not an absolute truth. There's an optimum rate for the equilibration. So you actually end up going from producing very nice single crystals to producing very twin crystals if you go too slow. But generally, you're going to produce smaller crystals if you equilibrate more rapidly. These are just some methods that can be used that are passive methods, placing a layer of oil on the surface of the reservoir solution, increasing the distance between the drop and the reservoir solution. All of these things can be done to slow down the rate of equilibration or potentially speed up the rate of equilibration by decreasing the amount of vapor space between the drop and the reservoir. And so this is just showing a quick example. These are some relatively small crystals, not small these days, I guess, that were grown using a standard vapor diffusion experiment, and this was using a gradient reservoir where we slowed down the equilibration between the drop and the reservoir solution. Okay, so something that can be very practical for producing smaller crystals. I was saying earlier that typically the reservoir solution is the cocktail solution, but it doesn't have to be. You can use anything that you want for the reservoir solution. It just has to dehydrate the droplet. And if you're trying to produce many small crystals, you might want to consider looking at approximately what the vapor pressure of the water or the reservoir solution is. Say it's a 2 molar ammonium sulfate reservoir. If you're producing a few larger crystals using that reservoir, you might want to consider using like a 4 molar ammonium sulfate reservoir. So it's going to dry out the drop more quickly, approach supersaturation more quickly, and potentially produce more very small crystals. And it's also going to drive it to a higher level of supersaturation. So if you have clear drops, replacing the reservoir with something that has a lower vapor pressure of water can actually pull more water from the drop, help the drop to concentrate, and sometimes give you crystals where you had clear drops before. So there's a couple of different ways that you can actually apply these chemical variables or change the concentrations of the chemicals that you have in your solution. So there are many different ways to do this. I'm just going to focus very quickly on 2 chemical sampling methods. Grid screens, which are very commonly used to optimize crystals, either to grow larger crystals or smaller crystals, and a drop volume ratio approach. So grid screens have been around for quite a long time. It's a really intuitive way to do the optimization experiment. It's easy to interpret the results. I'll show that in a few minutes. Before you set up the grid screen, you have to decide what kind of granularity you want to use, how fine a sampling you want to have, or pH, or the concentration of the precipitating agent, or whatever other variable you're planning to look at. Typically, if you're going to do a grid screen like this, you're going to have to prepare stock solutions, dilute them out. So it does take a little bit of time to prepare the solutions that are going to be used for this kind of an optimization. But again, it's very straightforward to interpret it and very effective. So in this case, we're just going to do a very fine sampling of the pH from pH 4.5 to pH 5.5, and a 2% change in the concentration of the precipitating agent, which was PEG 4000 for this protein. So you just you prepare these solutions, pretty straightforward. These are the results for this particular protein. And the thing I want you to notice right away is, first, a very slight change in the pH can have a huge impact on the outcome of the experiment. So this is pH 4.5, 4.6, 4.75. So you see you go from basically not having crystals or having these microcrystalline precipitates to actually having reasonable crystals or single crystal diffraction. And the same thing's true now if we look at the PEG concentration. By increasing the concentration of the PEG, holding the pH constant, again, you start to move towards smaller and smaller crystals, which could be very useful for producing crystals for XFEL's work. So if we just look overall now at this, and say we've got clear drops forming down here, we've got precipitated drops forming up here. These haven't been characterized to show whether they're amorphous or microcrystalline precipitates. We know we have crystals, visible crystals forming between those 2 boundaries. We know, because of the phase diagram, that we have basically lower solubility of the protein under these conditions, the lower pH value, higher concentration of PEG, have higher protein solubility at the higher pH values and lower PEG concentrations. So we can use this information to kind of design our experiments. So for subsequent experiments, if we want to produce smaller crystals, we want to drive things to this higher level of supersaturation. If we want to produce larger crystals, then we typically want to back away from these conditions and focus more on the regions that are at lower levels of supersaturation and do perhaps more fine screening there. What you can't see in this, but you can see if you use if you add artificial seeds or nuclei, is that the clear drops that are metastable will actually produce crystals if you add a nuclei to them. So you can actually map out the metastable part of the phase diagram by using seeding. So seeding will give you hits from some of these clear drops that are just going to remain clear without the addition of seeds. The final sampling method I want to talk about is just using a drop volume ratio approach in the cocktail. And Guillermo talked about this briefly this morning as well. So you can change the experiment drop chemistry without actually having to reformulate different cocktail solutions. And the way you can do that is just simply by taking your protein in your cocktail, and instead of just combining it in an equal volume ratio of 1 microliter protein, 1 microliter of cocktail, you can change the ratio. And when you do that, you change the chemical concentration of the drop. You're changing the concentration of the protein, the concentration of the salt in this case, and sampling along this path of conditions. And you might find that you produce the kind of crystals that you're trying to produce, whether they're large crystals or small crystals, at one extreme or the other extreme or someplace in the middle of these drop volume ratio evolutions. So you don't have to just do 3 drop volume ratios. This is an example where we actually did 16 different drop volume ratios. Again, you have an equal volume ratio here in the middle, and then you sample up here where you have a very small volume of cocktail, large volume of protein, down to over here where you have a larger volume of cocktail, smaller volume of protein in the drop. So it's a very complex sort of chemistry that you're doing here, because there's going to be micro changes across this in the concentration of the protein, the concentration of the chemicals in the cocktail, the pH of the solutions. And the protein is never just the protein, right? It's always got some other chemicals in with it to stabilize it. So you're also changing the concentration of those. So if you were to try to sort of make up these solutions and tell somebody, I want you to make up this particular solution with these chemical conditions, it would take them quite a long time to do it. But just doing a drop volume ratio of the cocktail solution and the protein solution, it's very quick to do this, and it's very reproducible to do this. So this is just taking a protein that was used for crystallization screening that produced microcrystals, and just doing the volume ratio, okay? So again, large volume of cocktail, small volume of cocktail, large volume of protein up here, and down here, large volume of cocktail, small volume of protein. And it's just a smooth incremental change in this. And the reason I wanted to show this to you guys today was, if you're trying to produce small crystals, this is just the SHG signal. You can see that using this drop volume ratio method might not be such a bad way to go to try to optimize these small crystals instead of growing large crystals and crushing them, because you are actually sampling different levels of supersaturation, and you can see from the SHG signal that you're producing some real differences in the outcomes of the experiments. So some of these may be more suitable for diffraction on the XFEL than others would be. Now, if we take the protein concentration and we cut it in half, just dilute it with the protein buffer, and set up those same 16 experiments, then you get very large crystals forming. The diameter of this well is about 0.9 millimeters. So we're able to produce very large crystals, and that's the same experiment that you saw on the previous slide, except this time we started off diluting that protein concentration in half, okay? Which, again, is going to drop the level of supersaturation. So if you think about what we're doing with these 16 drop volume ratios, we're just sampling this sort of path, which can be a very linear path if you're looking at it just in terms of protein concentration and cocktail concentration of chemicals, or even the volumes, right? It's a very linear volume ratio. But you're going to get some specific outcomes that come from different points along this path. Okay, so even though it might be very complex chemically to figure out exactly what the pH of that solution is, what the concentration of every chemical that's in that solution is, practical point is, if you just look at these results, it's very easy to sort of figure out where you fall in a phase diagram, right? So we know that the drops that are heavily precipitated, we can identify those as being here. If we're forming crystals, we're someplace in the Slabile region. If we're not seeing any crystals forming, then we're someplace either below the metastable line, saturated, undersaturated. So although we don't know exactly where we're falling in the phase diagram, we have a good idea of what region we're falling in the phase diagram, and that can inform subsequent experiments. So again, this just sort of ties it together, but it's difficult to figure out exactly what's happening when you're relating it to something that's shown in 2 dimensions in a very simplified cartoon form like this phase diagram representation, when you're trying to represent multidimensional chemical information. But just having the information from this is enough for you to figure out where you're falling in a phase diagram, which can help you design your subsequent experiments. I'm not really going to talk about this, just briefly, but if you're thinking about producing very small crystals, you do have to be aware of Oswald ripening. So basically, these are microcrystals, and very shortly after forming, larger crystals will start to appear in the drop because the smaller crystals are thermodynamically less stable, and the smaller crystals basically go back into solution and end up feeding the bigger crystals. So it's just something to be aware of if you're working with very small crystals. That's plenty of that. So summary, this was a very, very extremely limited talk on optimization. And it's just a very sort of complicated process. There's a lot of different methods out there available for it. Most of the methods that people use in the literature are going to talk about producing larger single crystals instead of producing smaller crystals, which is the goal for the XFEL's work. But a lot of these same methods can be applied to produce smaller crystals. If you just think about what they're doing and sort of reverse the goal of the original experiment. So instead of slowing things down, you speed things up. Okay? Crystallization method, again, is going to have a pretty big impact on which variables you can actually sort of address for the experiment with regard to supersaturation. Outcomes are going to change over time, so especially in the case of Oswald ripening. One of the big things that I think, well, people generally pay attention to this when it doesn't happen, but you want to be able to reproduce your hit, okay? So whether you're trying to grow very large crystals or very small crystals, the important thing is that you have a protein that's well characterized. You go into crystallization trials knowing that that protein is going to remain relatively constant in the preparation protocols. And if you're producing crystals from that particular protein, purified that particular way, you want to keep things constant so that you can reproduce those hits again during subsequent optimization experiments or production experiments to produce crystals for actual diffraction. So being able to reproduce the hits, whether it's the sampling method that you're using for the optimization, whether it's DVR or grid screens, that's part of it, but the other part is making sure that your protein is being taken care of the same way, and that's not always an easy thing to do. So thanks for your attention.